Here is the forward state space search algorithm. This algorithm is defined as a function forward search that takes three arguments, namely the three components that make up a planning problem. The first component is the set of operators defined for the planning problem. Then we have an initial state and a goal description. The algorithm works by starting from the initial state and searching from here. And it also builds up a solution plan while we'll go through this loop. As for the previous search algorithms, the first thing in the loop we do is test whether we have reached a goal state. The goal test now is whether the state that we're currently looking at, initially this is the initial state, is a goal state. We test this by testing whether it satisfies the goal. If this is the case, then we can return our plan, initially the empty plan. So if our initial state was a goal state, then we return the empty plan and we're done. If not, we have to continue. And what we have to do next is compute the state transition function. We do this, as described earlier, by computing all the ground instances from all the operators defined in our planning problem that are applicable in our state. So this gives us the set of applicable actions in our current state. Now, if this set was empty, if there are no applicable actions in the current state, then we can return failure. That means we have exhausted our search space and haven't come across a solution. The next step is to simply choose one of the applicable actions that we have just computed. What I've done here is simply made my life a little simpler by describing the algorithm as a non-deterministic algorithm. This is a non-deterministic choice point. What this means, any actual implementation would have to do search here, it would have to backtrack to this point to try out a different action if the one we've chosen previously fails. So this would build up a search tree branching at exactly this point. In a non-deterministic algorithm, we can of course assume that we have chosen the right action here. Then what we do is we simply update our current state by applying the state transition function of the previous state, this is the previous state, and the action that we apply in this state. And of course we have to add this action to the plan, so we concatenate a new plan consisting of just one action to our old plan and get the new plan as a result. And that's it. We simply go through our loop again until we either come to this point where we can return a plan to a solution state, or we come to this point where we return failure, meaning we have exhausted the search space and didn't find a solution. And here is a very simple example to illustrate this algorithm. We start off in initial state, which is the trivial problem we've seen earlier, and we've defined the goal, also from the example we've seen earlier, to give us just one state as a goal state. But the algorithm doesn't know that there's only one goal state or where it is, so we will remove this here. So the first thing the algorithm does is test whether this is a goal state, and I can assure you it is not. So the algorithm will continue by computing the applicable actions and then selecting one of these applicable actions. And in this case, what the algorithm does is select this action here. We're taking with the crane, there's only one, at location 1, the container, which is on this pile here, from the pallet in the pile. That is the action that the algorithm chooses. Then what happens is it applies the state transition function to get a new state, which is the state we see here, and it also updates its plan, which is what we have here. And it continues like this through the loop, so it checks whether this is a goal state, it isn't a goal state, it computes the applicable actions, picks one of those. In this case, that's the move action, and accordingly has to compute a new state. That's the new state we generate with this move action, and so on. We continue through the loop and see this is not a goal state. So we compute the applicable actions again. Now we try to load the container with the crane at the location. And we get a new state as a result. Now you can see the container is on the robot. And this is not a goal state, so we go through the loop and we find there's a final action that we need to execute. We need to move the robot to the other location. And then we get a new state, and this is now our goal state. So at the beginning of the loop, the algorithm will terminate. And it will return at this stage this plan here, consisting of those 4 actions that gave us the path through this state space. So you have seen that the algorithm was only a very small step given all the definitions we had before. But now we want to say a little bit more about the algorithm. And what we want to say is that the algorithm possesses 2 properties that are very important. Forward search is sound and forward search is complete. Soundness means that if the function returns a plan as a solution, then this plan is indeed a solution. This is of course a very useful property of such an algorithm. If the algorithm was not sound, that means it could return a plan that isn't a solution, so we would still not know what the solution is. But the algorithm is sound. And the proof of this is very simple. We can show this by induction, and we show that at the beginning of the loop, this statement here always holds. So we have the two loop variables, state and plan, and we show that the state is always equals to gamma of Si and the plan we're currently looking at. This is true initially, of course, because the initial value of state is the initial state, and the initial plan is empty. So gamma applied to Si with the empty plan means we still are in the initial state, and those two are equal. And then we can show that this condition is maintained through the loop. Each iteration of the loop keeps this condition true, which means it is also true for the final iteration before we return the plan, and that means the state is the result of applying the state transition function in Si with the plan. And we return from the function when state satisfies the goal, so therefore this plan must reach the state, and our algorithm is sound. The second property, that the algorithm is complete, means that if there is a solution to our problem, the algorithm can find this solution. And since this is a non-deterministic algorithm, we talk about an execution trace. So there is a set of choices that we can make at the non-deterministic choice points such that the algorithm will return the solution plan. And again, the proof can be done by induction, and this time we show that our plan is always a prefix of the plan we're looking for. What you need to remember is only that our algorithm is sound and complete.